You ever see a giant crane lifting something super heavy and wonder, how in the world does that not just tip right over? Or, those cool mobile sculptures that just hang there perfectly still? Well, it's not magic, it's physics, and it goes way beyond a simple seesaw. Today, we're going to dive into the principle that explains how anything with a whole bunch of forces pulling on it can find its perfect balance. So, here's our game plan. We'll kick things off with a balancing act we all know. Then, we're going to level up and tackle the main principle for juggling lots of forces. After that, we'll see how you can actually test this stuff for yourself. And finally, we'll talk about why this concept is so important, way beyond the playground. All right, let's start with something familiar, something we've all seen, probably even played on, the seesaw. It seems like kid stuff, but honestly, it's the perfect way to set up the much bigger puzzle we're about to solve. Okay, so one person on each side of a seesaw. Simple enough. But what happens when more friends jump on? All of a sudden, you've got different weights at different spots. How on earth do you figure out where that tipping point is now? How do you keep the whole thing from crashing to one side? That is the real question, isn't it? The secret sauce here is a little something called moments. Now, a moment isn't just about how heavy something is. It's about the turning effect that weight creates. And crucially, it's a combination of both the force, the weight, and how far away it is from the pivot. Getting your head around this idea of a turning effect is absolutely key. So how do we take this idea and apply it to something more complicated? Well, it's time to upgrade the basic principle so we can handle situations where there are a whole bunch of forces all working at the same time. And here it is, the big one, the principle of moments. Now, the two most important words in that whole definition are the sum of. That's the real game changer. We're not just comparing one force against another anymore. No, we have to balance the total turning effect on the clockwise side against the total turning effect on the anticlockwise side. Think about it this way. If you have two people sitting on the right side of the seesaw, they're both trying to make it spin clockwise, right? They're on the same team, so their individual turning effects, their moments, they actually team up. You have to add them together to figure out the total clockwise turning power. And you know what? The math here is actually pretty simple. So look at the clockwise side. We calculate the moment for the first force, force times distance. Then you do the exact same thing for the second force. To get the total clockwise moment, you just add them up. And you do the exact same thing for all the forces on the anti-clockwise side. It's really just about adding up each team's total effort. So here's the bottom line, the thing you have to remember. For that seesaw or a bridge or a crane to be perfectly balanced, what scientists call being in equilibrium, the grand total of all the clockwise moments has to be exactly equal to the grand total of all the anti-clockwise moments. The two sides have to fight to a perfect draw. Now, theory is one thing, but physics is all about seeing it in the real world. So how can we actually prove this principle works? Well, it turns out it's surprisingly easy, and it's a fantastic way to see this whole idea in action. The main goal here is to prove that when something is balanced, there's no resultant moment. Okay, what does that mean? Think of a resultant moment as the winning turning force. If a system is balanced, well, there is no winner. The clockwise team and the anti-clockwise team have canceled each other out perfectly. Nothing moves. And you could totally do this at home. First, you just balance a ruler on a pivot, like a pencil. Then you hang a few different weights, maybe some coins on each side. You just slide them back and forth until that ruler is perfectly flat and still. That's equilibrium. Then, for the cool part, you measure all the distances, you do the math for both sides, and you should find that your two totals are pretty much identical. And when you do that experiment, you're making this principle real. When you see that ruler just sitting there, perfectly balanced, you're literally watching a state where all those competing turning effects have perfectly canceled each other out. It's like physics in perfect harmony. Okay, we've covered the theory, we've even talked about how to prove it, so let's wrap this up. What are the really important things you should walk away with? All right, let's lock this in. First, equilibrium is just the physics term for perfect balance. The golden rule to get there, the total clockwise turning has to equal the total anti-clockwise turning. Simple as that. And this works no matter how many forces you're juggling. When this balance happens, the net turning effect is zero. And maybe the coolest part, this isn't just some abstract idea. It's a real physical law you can test for yourself. So, I'll leave you with the thought. This one principle governs everything from how a skyscraper stays standing to how a gymnast holds a pose on a balance beam. Now that you get it, now that you know how to juggle multiple forces, start looking around. What things, big or small, do you see a little differently now? Thanks for tuning in.